Yes, sir, it is visible, sir.
Okay.
Again, now it is not visible, sir.
Okay, I will do it.
నువ్వు చెప్పాలి ఇంకా రా చూపించాను కొట్టినా ఆడ రికార్డ్ అయిందా ignore
Ignore.
IGNO
Yeah,
below ignore yes sir, that one yes yes sir
awesome.
Good afternoon to one and all.
Good afternoon.
Sir, shall we start, sir?
Yeah, as you like. If there is time, no
Okay.
problem.
Yes, sir. Yes, sir. Good afternoon to one and all. Today, our next session is on green composites. This session will be taken by my guru, like I can say, Professor A. Varadarajulu Garu, who is the retired eminent professor from SK University, Sri Krishna Devaraya University. Before going to say that he is the key pillar in establishing the Department of Polymer Science and Technology in SK University, Anantapur, in last 2 decades before. At present, Sir age is of around 71 years. Still, Sir was with more enthusiasm continuing in his research work. By this, we can understand his passion about teaching and research work. The morning session, which was taken by Dr. Ram Subbareddy Garu, is also a student of Varadarajulu sir. So, I think this is much more enough for us to give brief introduction about him. So, I request sir to give a small lecture from 2:15 to 4:15 on green composites as the present market. I can say one small word, as the present situation outside is more dependent and focusing on biodegradable one. So how this biodegradable one is linked to green composites, and what is this that sir in his class is going to explain to you. So it will be, I feel that it will be a wonderful class from sir. So thank you sir for providing opportunity to come and speak to the students or to the participants. Sir, now you can continue, sir.
Thank you. Thank you, Dr. Damodar. So at the outset, let
Thank you.
me thank Dr. Damodar for giving me this opportunity to share some of our experiences in this field of biodegradable, completely biodegradable composites and nano composites for packaging and medical applications. Actually, before this, we made many composites. For example, for space applications, we had carried one ISRO project, Indian Space Research Organization project, and then we developed a composite for the space launching vehicle, which is nearer to the fuel, which requires more strength and then higher thermal stability. For that, we used the phenol formaldehyde PF108 and then silica fabric that was made by ISRO itself. So, but that work was going on well, but we thought these materials will not be used by common man. Only for high-tech applications they will be used. Then we thought, why don't we make some materials for common man? That's
Sir,
why,
sir, one small
yeah,
interruption,
yeah,
sir.
please.
Just to please keep the mic somewhat in front of you so that we can able to hear
Okay.
louder, sir.
Oh, now,
It's
hello?
good, sir. Yeah, it's
Okay,
fine,
okay.
sir.
Okay. So then we thought, why don't we prepare some composites for common man? But most of these polymers, as you know, are non-biodegradable, so they pose many problems. Then we thought, why don't we make some polymers which are totally biodegradable? And the story started like this for this particular topic. So, where is it? Are you able to see it?
No, sir, I can't able to see.
Okay, okay.
Go for present now, entire screen, then
Yeah, now I will go. Entire screen.
uh, click OK, sir.
You must grant permission in order
Your
to.
entire screen means then you will get one screen. On that screen, press something, press your cursor and share.
Here there is one dismiss is there. Cannot share your screen. You must grant permission in order to screen share.
Just entire screen.
Your entire screen you press, sir. Present now, your entire screen.
Entire screen.
Then you will get one small window.
But I am getting cannot share your screen. You must grant permission.
Click on that.
Click on that, sir. You need to click on that screen.
But not.
Chrome wants to share the comments of your screen with Google, with meet.google.com, like that it will come.
No, it's showing dismiss like that.
Dismiss, sir. Dismiss. Again, again go. Now again I will tell, sir. In that there will be a small arrow mark.
Yeah, arrow
On
mark.
that on that you can able to see your entire screen
Not showing.
when you press it.
Yeah, yeah. Present your entire screen. I pressed it.
Then what you are getting, sir?
You must grant permission in order to share screen. Screen share. What is that? Earlier it came, but not now.
Relogin open also.
But you have to allow for share screen like that.
No, sir. From your side only you can able to share that.
Present now. Your
Present,
entire
yeah.
screen.
Yes, sir. Press it.
I pressed it. But you must grant permission like that. It is showing again.
Okay. One thing I will do, sir. I will leave this. You can leave the call and again you can rejoin, sir.
Yeah. Better.
That will be better.
Yeah.
మామూలు ఎవరైనా అంతే
There, like no. Designer.
No. Yes, sir. Can you able to hear me, sir?
Unmute.
Varadaraju sir, can you unmute it? Hello.
Hello.
Now I can
Unmuted.
able to hear you, sir.
Okay. Now I am getting a select window screen. Entire
Your
screen.
entire screen.
Yeah. Now
When
are you
you
able to
press
see?
when you press your entire screen, there you can able to have one small screen, sir.
Yeah. I'm seeing it. Mute website
Then you
notification
press,
while sharing.
just you press on that screen, sir,
Okay.
with cursor,
Okay.
and then share.
The cancel button, sir. Cancel button.
Now you got it, sir?
Yeah. Are you able to see it
No, sir, I can't able to see.
now? Hello.
No, sir. No, sir. No, sir.
But why? You are sharing entire screen.
Now it is coming, sir.
Now coming?
Yes, sir.
Okay.
Yes.
Okay then.
Yes. Yes. Now happy,
Oh,
sir.
now?
So you can.
Okay. Yeah. I'll go
Excellent.
quickly because there is loss of time.
Okay, sir.
So I also work in Thailand and China as visiting professor. Once in 6 months I go there, but not now because of this COVID. For the last 2 years I am not going there. So as I already stated, we prepared the material for this particular part. This is known as a nose throat part, which is nearer to the fuel. This we carried out in 2008 actually, and we were very happy. But unfortunately, there are many problems with these plastics. They are not biodegradable, but we use them very frequently. But the main culprits are the carry bags, unfortunately. What are the issues with these carry bags? Let me present briefly. There are many advantages. Why we don't carry cloth bag now, but we carry only plastic bags because they're lightweight, low cost, maybe 1 rupee or 2 rupees, or sometimes the shop wall gives free of cost. Ease of processing, very quickly you can make the bags. The manufacturing units, they make 5,000 bags per hour. So that is the rate of manufacturing. Low permeation to fluids. We can store even liquids or even gases cannot permeate, so pack them, pack the biscuits or some food materials so that they will be crisp. And attractiveness, you can make them with any attractive color and then print any design. But there are some disadvantages, for example, non-biodegradable nature, so they pollute the environment, choke the sewage pipes. It is very common in Hyderabad. Even for small rains, the drainage pipes will be choked because they're clogged with these plastic bags, so water will not go out. And health problems to animals if taken inside as food, because animals out of starving, sometimes they eat this, mistake it as a food material and they eat. Sometimes the cows and the cattle, they will be eating grass along with this. Suppose if there is any plastic bag, that also goes into their body and they kill ultimately. So this is a very common sight in many even small towns at the entrance. These bags will welcome us before you enter into the place. And spreading pollution because they're very light, as I already stated. So if there is a wind blowing, that can go anywhere. For example, if you leave this a particular plastic bag in Hyderabad, that will not remain in Hyderabad, and that can go to even Hong Kong also without any passport or visa because they can fly and travel long distances. So they spread the pollution indirectly, choking the drainage pipes. Sometimes these animals they eat, for example, out of starving. So what are the possible hazards? Intestinal problems and ultimately respiratory problems. That is why many animals are dying. So this flying bird encountered with a flying bag, carry bag, and ultimately out of suffocation, it died. It is very common sight in seashore. Moreover, these plastic films are made from polyolefins, so which are petroleum based. So the raw material is from the petroleum, precious petroleum. We do not know how long we can use the petroleum because it is a depleting source. So we calculated this in China because we carried out some work of collaboration with Chinese Academy of Sciences. So China will save 37 million barrels of oil each year. That means that much of oil is going into the production of this synthetic plastic film. Suppose if you avoid them, you can save so much of precious petroleum. So let me present this video on this. Sorry. This video on plastic pollution. Yes, it is a plastic straw. This cow has eaten 20 kgs of plastic. Yeah, what are the possible solutions? We recommend 4 R's. Restrict, do not use more. Reuse, if it is inedible, use the same bag many times as possible. Recycle, but it is not economical. So only 1% of the used bags are recycled in the entire world. Best thing is refuse. Or otherwise, if it is you are unable to go without plastics, then use biodegradable plastic films. So we are carrying out the following work. We are making completely biodegradable polymer composite films for packaging and medical applications. But there are some polymers already available, biodegradable polymers, for example, polylactic acid and polypropylene carbonate. These are synthetic or semi-synthetic polymers. But unfortunately, they lack strength. Sufficient strength is not there. Sufficient thermal stability is not there. but they're expensive also. So we have to modify them so that it will be affordable and they will have more strength, more thermal stability, and low cost, etc. We carried out some work in this direction. But what are the biodegradable polymer material? That is the matrix materials we used. Soy protein isolate. That is from the soy flour. We isolate the protein, or it is available commercially. And wheat protein isolate from wheat flour, polylactic acid, polypropylene carbonate, and cellulose. That is cotton. From cotton also we make the films. Polylactic acid starting material is sugarcane bagasse. So that's why it is a semi-synthetic polymer. Then polypropylene carbonate starting material is supercritical carbon dioxide. From polluting carbon dioxide, we make the polymer, polypropylene carbonate, which is biodegradable. Isolated proteins are, as we already stated, from soy flour and wheat flour. Cellulose starting material is cotton linters. We don't use the cotton because cotton is used for fabrics. So we use the waste of that cotton, which is adhering to the seed. It is known as the cotton linter, which is going as a waste. We use that waste for making the films. These are available commercially. So probably my student Dr. Subbareddy already gave you an introduction about the composite. So composite is a combination of two or more dissimilar materials. The resultant composite will have properties which are similar to those of the components. This already he has given. I'm not going into the details. So first we used the soy protein isolate, and then you used the natural fabric as a reinforcement, Hildegardia populifolia. This is available in Anantapur district of Andhra Pradesh, that is near Nallamada forest. Nallamada forest, not Nallamalai. There is another place, Nallamada. There is a small forest where this is available. So we have used this soy protein isolate as a matrix. Along with this, we used glycerol as a plasticizer and then glutaraldehyde as a cross-linking agent, because this is a thermosetting polymer, biopolymer. So this is a film we made. This is a composite film, SPA, glycerol plus Hildegardia. Hildegardia is a uniaxial fabric that is available, and Telugu name is Gali Buduga. The seed will be like a air balloon. So we studied its mechanical properties. The SPF matrix is having only around 24 megapascals, but when we have added this fabric and coupling agent, its strength has gone more than doubled, 53.16. So the polyethylene will be having a strength of 25 to 35 megapascals. So our film has exceeded that of the polyethylene itself, because we used a uniaxial fabric as the reinforcement and so on. Modulus increased from 947 to around 5,000 and so on. So these are superior properties when compared to the commercial polyethylene or polypropylene films. And then we studied its fractographs. So without untreatment, so generally whenever using the natural fabrics, it is better to remove the impurities and then hemicellulose part of it, because hemicellulose is a weak material, the surface material that can be removed by alkali treatment, that is 5% sodium hydroxide. If you dip it for about half an hour and then clean with water, that will be going to a larger extent. So here it's not having much strength, but when we use the coupling agent, but still that gap between this is a matrix and this is a fiber in cross-sectional view. This gap is the interface actually. So this is a large interface, But when we treated the fabric with sodium hydroxide, the gap somewhat came down, but it is not sufficient. So when we used the coupling agent, you can see that the gap narrowed. The interfacial gap is narrowed, and there is a matrix skin formation on the fabric surface itself and so on. So it leads to higher mechanical properties. And then we studied its biodegradation by soil burial test. Probably you might have covered this. So the biodegradation methods, we bury them in the soil and then weigh it for every 5 days and calculate what is the weight loss. Our particular film has lost 95% of its weight in 60 days. Within 2 months, it is almost degraded. And we prove this by this same images also. For example, this is before degradation, smooth surface. After degradation, the surface becomes very rough, and then the texture becomes loosened because most of it has been degraded and so on. Then we went for wheat protein isolate, and these are the constituents of this wheat protein. Maximum protein is 90%, fat 4%, ash, and so on. So this is a matrix film, whereas this is the composite film with the same fabric, Yildigodia, and the matrix was having so many wrinkles, but the composite is a uniform one. The matrix was having a strength of 14.5 megapascals tensile strength and 769 modulus and 48.3% of elongation. But when we treated the fiber and then used the coupling agent, the strength has gone to 67.49 megapascals, and then the modulus has increased to around 4,900, and the elongation came down to 2%, from 48 to 2%, which is required elongation for the carry bag purposes. Same thing we carried here also. It degraded within 60 days on soil burial. As long as you use them, they will be all right. But once you throw them into the soil, on the soil, that microbes in the soil, they will eat away that particular matrix, and then the fiber also, natural fiber also, and the biodegradation will be taking place. But then we thought these two materials are food materials, wheat protein and then soy protein. Then we thought, why don't we go for non-edible polymer, biopolymers? And cellulose is one such polymer, biopolymer, that is the cotton. And then we used cellulose as a matrix and some natural materials as fillers or reinforcements, and made the completely biodegradable composite films. But separation of the cellulose is a very big problem, because it degrades before its melting point. The only way is you can make it by solution method. For that we have to dissolve the cellulose. But cellulose dissolution is a very difficult problem. So the usual, or the industrially they used cuprammonium salt and carbon disulfide, so which are both carcinogenic. So now they are not recommending, but we developed our own solvent. So with safe chemicals, for example, 7% sodium hydroxide and then 12% urea in water, and then we cooled it to minus 12.7 degrees Celsius. You may ask me one question: will it require any special gadget to cool it to minus 12.7? Suppose if you have got a freeze, the deep freeze will go up to minus 15 degrees. So if you, in your laboratory, if you have got a freeze, you can keep this beaker in the deep freeze, and in 1 or 2 hours, the temperature comes to around minus 12.7. And that was used as the solvent for the cotton. We used 4% of the cotton linter, and I will show you the procedure here. So this is a pre-cooled solvent, minus 12.7, so 7% sodium, 7% 7% sodium hydroxide and 12% urea, and it is pre-cooled. After cooling, you can keep it outside and then add this cotton linter so to this solvent, and then stir it. You require a magnetic stirrer. It is available in most of the laboratories. Within 2 minutes, you will be getting a solution. Let me show this clipping. This is a real time what we carried out this synthesis of this particular solvent in Chinese Academy of Sciences. So this is a real time. I have added this cotton to that pre-cooled solvent at room temperature. Now stirring it, you can count down the time. Within 2 minutes, you will be getting clear solution. Yeah, within 2 minutes you can be getting. But whereas with it, industrial cupric solvent and then carbon disulfide, it takes 24 hours for dissolution. So for 24 hours, we reduced the time to 2 minutes. So preparation of the cellulose film, after getting that solution, suppose you want to make it as a composite, you add that material, a filler or a fiber, and then mix them together and then cast the film. But casting is again a difficult thing. We follow what is known as the regeneration method. We form the liquid film of the composite and then make it as a solid by using a non-solvent. So, because we used the sodium hydroxide, we use an acid as the coagulation bath to convert the solution into a solid. So let me show a clipping of how we prepare. Solution. It may be matrix or a composite. So this is how we make the composite films using cellulose. The first system we made was using waste silk fiber as the filler or the reinforcement in cellulose. This already we published in 2012. So this is a film actually, cellulose as a matrix, and this fibers you can see, it is a transparent film, silk fiber composite film and so on. For further information, you can go to this because we suggested this for the wrapping purposes, for example, flowers or any gift items and so on and so forth. And even if you throw them, they will be degraded within 2 to 3 months. Then for medical applications, we use turmeric powder as the filler, and we made the cellulose composite, cellulose turmeric powder composite film. This can be used for both packaging and then the medical purposes. So these are the films. We loaded up to 25% of this turmeric powder. You can see the increasing color, deepening of the color with concentration. So these are the flowers wrapped, the rose flowers wrapped with these films. And it is antibacterial also. And that is why the flowers remained fresh for about 1 week, which is not possible with ordinary packaging films because it is antibacterial. It did not allow the growth of bacteria inside that film wrap. And we also tested its anti-tumor properties because turmeric is very good anti-tumor tumor material. And here we tested for the anti-tumor property or cell viability for 2 types of cells. The red ones are the normal cell, and then the green is the TELSA cancer cell. We found that the cancerous cell growth was going down as a concentration of this turmeric powder was increasing, but whereas these normal cell growth cells were not affected, but they remained. So we recommend this particular film for skin cancer so that it can be wrapped around the cancerous skin so that the cancerous cells can be annihilated or killed. So what is responsible for this? The curcumin, which is 3% present in the turmeric powder, that will be doing the wonders. It is a coloring matter, not only coloring matter, but also it gives more, it is responsible for the medical properties. Then we thought, why don't we use curcumin directly so that we can make concentrated antibacterial film and so on. So then we made films of the cellulose and curcumin. So this work we carried in China, the Chinese Academy of Sciences, Beijing. So he is my collaborator. This is our laboratory. Our laboratory is in the 6th floor. So this is where I prepared these films here. So this is a wet film as we showed you. And then after drying, it looks like this, for example, yellow transparent film. And it showed very good antibacterial property. Antibacterial property, what we do is, first we take a gel and incubated this with bacteria, whatever the bacteria we select, and then incubate. That gives a cloudy film. And suppose if we introduce our film and place it here, this is our film with cellulose and curcumin, the colored film. And if you see it carefully, around this, the clear zone is formed. Clear zones indicate the killing of bacteria. Once the bacteria is killed here, the translucence will lose and then transparency will be observed. This indicates that around this, up to this portion, the bacteria is killed. The diameter is known as the antibacterial zone diameter. So the properties are good tensile strength and modulus, good thermal stability. Because of the phenol compound present in this, the thermal stability increased, showed antibacterial activity towards E. coli bacteria. And for further information, you can go for this, our publication in RSC Advances. Then we used neem leaf extract as the second component in cellulose, and we have taken 10% leaf extract and dipped it and then dried, and it also showed very good antibacterial activity against different concentrations of this leaf extract, and a very clear zone is formed. So this can be used as antibacterial packaging films, both turmeric and then this neem extract films. And another advantage is they're biodegradable. They're antibacterial as well as biodegradable and so on. But then we thought, why don't we use some waste materials as the fillers so that the cost of these composites can be brought down. So we used the eggshell powder as the filler. We also used tea leaf powder. After brewing tea, we'll throw away, but that can be dried and then made powder, and that can be used as a low-cost filler. We used PPC and PLA as the matrix materials and also cellulose. Let me show some of the systems we prepared in this direction. So we followed the casting method for the polypropylene carbonate and then polylactic acid, because we don't use the regeneration method but only the film casting method. So we cast the film, give a shape of the film for that composite solution, allow the solvent to dry and peel off the film. So like this we spread it. This is the liquid film, allow it to dry, and after that you can peel off the solid film. So polylactic acid and eggshell powder. This is a polylactic acid matrix, white one, and inside it, these are the eggshell powder particles. We loaded up to 5% eggshell powder. So they showed very good strength and then thermal stability, because calcium carbonate, eggshell powder is nothing but 95% calcium carbonate, so which is highly thermal stable. So the strength has been increased because it is a rigid material. I'm not presenting the data because lack of time. Suppose if somebody is interested, they can go through our publication on this particular one, which gives all the information. Then we used it in the polypropylene carbonate, another biodegradable film. These are the particles. This is a transparent film with this eggshell powder filler. So fractographs are also taken. Additional information you can get through this particular publication. Then we used this in used tea powder, because used tea powder has got these particular components, proteins, amino acids, polyphenols, tannins, etc. They will not be go out. Even after brewing, they remain there. So we used this in the polypropylene carbonate. So very uniform film here. Sorry. This we already published. They gave very good strength and then the higher thermal stability because of the presence of the polypropylene carbonate. Moreover, it lowered the cost because it is a waste material we used, and the cost has come down. Then we used this in the cellulose matrix and made the films here. And this can be used as a packaging material. We found an additional application for this composite film with this spent tea leaf powder, because it is the tea leaf powder has got the ability to absorb the dyes. So for example, here we used a methylene blue here. So we dipped this film in methylene blue solution, and we have seen that the entire methylene blue dye was uptaken by this film. So this can be used for the purification of the industrial wastewater where the dyes are used. For further information, you can go through this particular publication here. But then we thought, why don't we make some nano composite films, biodegradable nano composite films, especially for antibacterial applications in medical field. But there are two methods of making these nano composites. First thing is you make the filler separately, nano filler separately, and then take a polymer matrix and then disperse it in it. This is one method. This is by dispersion method. But unfortunately, this dispersion method is a two-process method. Not only that, the dispersion is not uniform. At many places, you will be getting the agglomeration so that the composite will not be uniform. In order to avoid that, we devised our own method of in situ generation of these metal nanoparticles inside the matrix. Instead of making them outside and then disperse, we generated the particles inside the matrix itself so that it will be a single method process, namely in situ generation of these nano materials inside the matrix. We made both the films and then also fabrics, nano composite fabrics for hospital applications. But what is nano? Nano is not an English word, but it is a Latin word. So in Latin, nanus means dwarf, very small. So in 1960, the nanometer is defined as 10 to the power of -9 of a meter. And because the size of these nanomaterials will be of 10 to the power of 9 meters, so we call them as the nanomaterials. Any material whose at least one dimension is 1 to 100 nanometers is known as the nanomaterial, as already discussed by Dr. Reddy in the morning. But these nanomaterials will be divided into three types: zero dimensional, one dimensional, and two dimensional. Zero dimensional materials are nanoparticles because we cannot measure the length or width or dimensions. So we call them as, practically it's not true, but for all practical purposes, we call the nanoparticles as zero dimensional because the dimension is very, very negligible. One dimensional material is nano wires or nano fibers or nano rods. They will bang the length but not the diameter and so on. But two dimensions are thin films and layered structures. For example, mica or the clay, they're the layered structures. But we concentrate on metal nanoparticles because our purpose is to make the composites at a reasonable price with low cost equipment and so on and so forth. The main characteristics of these metal nanoparticles are large surface area to volume ratio as compared to their bulk equivalents, large surface energies, plasma exciton. So they show the absorption in the visible range, antibacterial activity. But are these metal nanoparticles new? No. They have been used from times immemorial in sculptures and paintings, even during the 4th century AD. So they're so old. Sorry. What is the proof? So the extraordinary cup, this is a Lycurgus cup actually. This was used by the Roman Empire Lycurgus in 4th century AD. This is a cup. This is the picture of this Lycurgus. It is a wine cup. So what is the peculiarity of this cup? This cup is actually given a light green color. This painting actually on this cup and with the metal carving outside. The peculiarity of this cup is, suppose if you illuminate this in the uh, axial direction, it appears to be light green. Suppose if you pass the light into the cup, for example, suppose if you illuminate the cup in this direction, you see it green. But once you illuminate the cup from inside, the color changes to rose or pink and so on and so forth. It is known as the optical dichroism, which is a unique property for this metal nanoparticles. But at the time, it was not proved that they are the nanoparticles. So now it is established that they are made up of two metal nanoparticles, silver and gold, of around 70 nanometers, and the ratio of the silver and gold was 14:1. In 4th century itself, they made this nanocomposite. Another classical example is the cathedral churches, Gothic European cathedral churches in France, for example. So this is the roof and then windows of different colors. These colors are made up of these nanomaterials. For different colors, they use different metal. And then for different colors, again using the same metal, they varied the size and then obtained the required color. So which is amazing in those days. And the color depends on the metal, its a size, its a size and shape. You can make different sized spherical, triangle, hexagonal, and so on and so forth. As the size changes, size and then shape changes, the color also changes. But why we are interested in only in 21st century, but not earlier? Though these materials were prepared long back, there were no instruments to prove that they are nanomaterials, because the transmission electron microscope was invented in 1931, whereas the scanning electron microscope was invented only in 1937. So in 4th century, these instruments were not there. So that is why, because these are not visible with our naked eye. So even ordinary microscope we cannot use. At least you require the SEM or better TEM and so on and so forth. But now they are available. So now they established that those paints though used in 4th century, they're nothing but the nanocomposite paints. But in our laboratory, we don't use any synthetic chemicals to prepare this nanocomposite films and fabrics in our laboratory. Our main aim is to use safer materials at lower cost. So we don't use sophisticated instruments to prepare these composite films, but we use only those materials available in the laboratory, or they can be purchased at low cost, and so on and so forth. Well, so we used cellulose as a matrix to start with, and various plant materials, leaf extracts as the reducing materials for making these nanocomposites. What is the reducing? Bioreduction means to reduce the metal salts into their corresponding metal nanoparticles. So, but here we follow only the in situ generation method, as we already stated. Why leaf extracts? Leaf extracts themselves will have so many chemicals, biochemicals. So we need not go for synthetic chemicals. And these chemicals will be having hydroxyl groups, polyphenols, tannins, flavonoids, etc., which are very good reducing agents to reduce the metal salts into their corresponding metal nanoparticles. What leaf extracts we used in our laboratory? Osmium sanctum, that is tulasi, neem, pinnata pongania, that is kanuga, cassia alata, terminalia catappa, aloe vera, vitex, moringa drumstick, red sandals powder, tamarind leaf, etc. We used so many leaf extracts. Let me present some of the systems we made using these leaf extracts. So we follow 4 steps in this particular preparation. First is the preparation of the leaf extract. So because this is the reducing agent actually. So what we do is we take 10% leaf extract. That means suppose if we want to make 1 liter of this leaf extract, we take 900 cc of the deionized water and then 100 grams of this finely cut leaves, cleaned and cut leaves. Whatever leaf you want, you can clean them, dry them, and then cut them into pieces. And then heat this deionized water to 80 degrees Celsius and introduce these leaves and maintain that at the temperature for 20 minutes. So you'll be getting the extract, that extract of these chemicals into the water, and we call it as a leaf extract. So this is illustrated here. This is the water at 80 degrees, and then these leaves were added here, 10% leaves, and we allow it to for 20 minutes and then filter, and this is the leaf extract. So in the first step, we made the leaf extract and then allow it to cool and keep it in a refrigerator until it is used. In the second step, preparation of the matrix. Suppose if we want to use this cellulose, as you already presented in the biodegradable composite films, we make the solvent and then use the regeneration method, as I already pointed out. So this is a solvent, and then we use the regeneration method. So what are the advantages? It's simple method, rapid method, and no toxicity. But for other things, we use the film casting method, as I already stated. In the third step, making the matrix. Actually, we made the cellulose wet film. We need not dry it. Now what we do is, we dip this wet film in this leaf extract. In the first step, we made the leaf extract. In the second step, we made the cellulose wet film. In the third step, we dip this wet film in that particular leaf extract, and then allow it on a magnetic stereo at room temperature for 24 hours at moderate 500 RPM. And as a result, this leaf extract will be diffused into the cellulose wet film. So making the matrix, this is the leaf extract, and this is a wet film here, and then 500 RPM. After 24 hours, take it out. And this is the matrix still in the wet form itself. In the fourth step, we have to regenerate we have to in situ generate the metal nanoparticles. For that, we have to prepare the salt solution, required salt solution. Suppose if we want to generate silver particles, take silver nitrate in water, because it is water soluble. So water is in different concentrations, 1 millimole to 5 millimole concentrations. And in each solution, you dip this matrix film Matrix film is nothing but the cellulose along with this infused leaf extract. So this is the process. So we are taking the metal salt solution here, metal salt solution, and then introduced this wet film, matrix wet film, and then on a magnetic stirrer at room temperature. Entire process made at room temperature here, and for after 24 hours, take it out and then dry it. We'll be getting the dry film. Same thing explained here. So the process in nutshell is cellulose wet film or cloth. It is white in color or colorless. Matrix is light brown to yellow, and then after dipping it in this, the nanoparticles will be generated because there is a leaf extract compounds inside the matrix film, and they react with this metal salt solution which is entering into that particular matrix react. So this matrix itself will be acting as a as a as in a laboratory, and then the reaction will be taking place between this leaf extract and then metal salt solution inside the matrix, and then the metal nanoparticles will be generated. As a result, the color of this matrix will change. So the change in color is a preliminary indication of the formation of this metal nano composite film. Sorry. After that, we have to characterize. We use the techniques TEM, SEM, FTIR spectroscopy to study the interactions between the metal nanoparticle and then the matrix. The XRD to prove the nature of this metal nano metal. Then TZA to see the thermal stability, antibacterial test, and then tensile strength test for some systems and so on. So first we generated silver nanoparticles using Osmium sanctum or the Tulsi leaf extract. This Tulsi leaf extract will be having eugenol as the main component, which is a very good bio-reducing agent. So this is the cellulose film, which is colorless, and this is a matrix along with this the leaf extract, and these three are the composite nano composite films with 1 mm, 3 mm, and then 5 mm silver nitrate solution. So you can see the color change between the matrix and then this nano composite films and so on. But how to prove that nanoparticles are generated inside? For that, you can go to the TEM analysis and then SEM analysis. The beautiful spherical nanoparticles are formed inside. So these are the spherical nanoparticles. And how to prove that they belong to the silver? For that, we go for the EDX, which is the attachment to this SEM itself. So this is nothing but energy dispersive spectrum. Actually, different metals will be having different energies. So this particular peak is showed by the EDX spectrum, which corresponds to the silver metal. And then we measure this size of these nanoparticles using the inbuilt software of the instrument itself, which is known as the SmartIF program. Using the SmartIF program, we measure the particle size, and then particle size distribution is given here. And most of the particles are between 60 to 90 nanometers or 60 to 100 nanometers. So and so they're very suitable materials for to be tested. And using this X-ray also, the matrix did not show any peaks, but whereas the nanocomposites, they showed some additional peaks, which correspond to the metal nanoparticles. So using the SEM, TEM, and then XRD, you can prove the presence of these nanoparticles inside this nano composite films and so on. Later, we tested the antibacterial activity. The matrix did not show any antibacterial activity. This is a matrix film, but no clear zone was formed. But whereas this is the nanocomposite films of 1%, 3%, and 5% silver nitrate solution, source solutions were used. And you can see that clear zones were formed with increasing diameter, with increasing source concentration here. So these showed very good antibacterial activity. As a result, we suggest them for as a dressing material, dressing film, for example, wound dressing film, and it can find medical applications in this way. And at the same time, we can also use it as antibacterial packaging film for wrapping purposes or for food packaging purposes and so on and so forth. But what about this diffusion of this particular metal nanoparticles inside the food? But we tested that after several washings, the particles stayed inside because the particles are held by the matrix, because there are OH groups in the matrix cellulose which are having negative charge, and this metal nanoparticle is having the positive charge. As a result, there is an electrostatic attraction between them. As a result, they are held permanently by these electrostatic forces inside the composite. So the coming out of these particles inside into the metal, any food material, is very minimum and so on. It may be in tolerant stages only. Sorry. So this particular work was already published in 2016. Sorry, 2016. So suppose if somebody wants additional information, because I have not covered all the properties because of the lack of time. The main properties are presented here. But then we generated copper nanoparticles because silver is expensive. So we want to reduce the cost of this particular nanocomposite films. So in the similar manner, we prepared the nanocomposite films with cellulose. This is a cellulose, this is a matrix, and these are the nanocomposite films with prepared with source solutions, copper sulfate source solutions of 25 millimoles, 125 millimoles, and then 250 millimoles. As the concentration is increasing, the color also deepening, and the color change here from the matrix to the nanocomposites preliminarily indicates the formation of these nanocomposite films. So this is the TEM analysis, spherical nanoparticles, SEM analysis, spherical nanoparticles. And then this is the, EDX spectrum showing the copper element here. And this is the particle size distribution. XRD also showed additional peaks corresponding to both copper and then copper oxide nanoparticles. So both the copper and carbon oxide metals are there in nano form. So with the size range between 60 and then 90 nanometers. They showed very good antibacterial activity with clear zones around this film, indicating good antibacterial activity. So this we published in 2016 itself. You can find this in Carbohydrate Polymer Journal, this particular one. So then, because it takes at least 24 hours for making the nanocomposite in the laboratory. Then we thought, especially for silver, because it is a photochemical, we thought, why don't we reduce the time by carrying out this entire process in sunlight? So that is why we already prepared these films in the laboratory for 24 hours for making the nano composite. And then we carried out the same experiment in the presence of this particular sunlight. So within 2 hours, we could get this particular films with in the presence of the sun. This absence of sunlight, and this is the presence of sunlight. This is a matrix here. What is a photochemical reaction? This is present here. So it acted as sunlight is acted as a catalyst and as a additional energizer, and then it hastened the in situ generation process. So this is in the absence of the sunlight, and this is the presence of the sunlight. In the presence of the sunlight, more nanoparticles were formed with the increased intensity of this silver, because more nanoparticles, and then the peak of this EDX spectrum has increased when compared to in absence here. In absence of the sunlight, in presence it is more number of particles are formed, and then distribution is somewhat narrower when compared to the wide distribution in the absence of sunlight. So this is how we reduced the time. This also we, and these are the XRD spectra absence of the sunlight, and then in the presence of the sunlight. So this also showed the peaks corresponding to the nano composites, and they showed this is absence of sunlight antibacterial activity, this is presence of sunlight. The diameter is increased when we carried out because more number of particles are generated in the presence of the sunlight. So this we published in 2017, 4 years back, effect of sunlight on the preparation and properties. Sorry, somebody is interested, you can go through this publication for additional information. Then we use another leaf extract, Cassia alata leaf extract. This leaf is known as Tangedu, which is very famously used in Batukama festival. So in another 2 days, Batukama festival starts in Telangana, so which is a unique festival. And this particular leaf has got many chemicals, biochemicals, and it has got many medical applications also. This Tangedu or Cassia alata leaf has got many medical applications. So we used its leaf extract as a bio-reducing agent because it has got many these particular chemicals, several biochemicals, which can reduce the metal salts into their metal nanoparticles inside the matrix, in situ generation. We are not generating outside, but we are generating inside the matrix itself. So this is the cellulose and then matrix. This is the matrix actually, and then so these are the composites with silver of different concentrations. So color change indicates the formation of the nanoparticles inside the matrix or inside the composite. This is the TEM picture and this is the SEM picture. So beautiful spherical nanoparticles are formed. And this is the antibacterial activity. So this also showed very good antibacterial activity. We published them in 2018, 3 years back. If somebody is interested for additional information, you can go through this publication. Then we used this Terminalia catappa leaf extract because that is nothing but the Indian almond or badam. Though this particular leaf is having quercetin as the main chemical, we prepared the leaf extract using this leaf and used this as a bio-reducing agent. This is a matrix and these are the composites with the silver nitrate. This is a TEM and then this is a SEM here. And this is a possible mechanism how this leaf extract is converting the metal salt into the corresponding nanoparticles. So metal nanoparticles here. So this is shown here in the mostly chemical intermediates are formed during this particular process. So this is a antibacterial activity here. This work was also published in 2017. If somebody is interested for more information, you can go through this. Then we also generated copper nanoparticles using the same leaf extract of Botham's Terminalia catapa. This is a matrix and these are the composite films. This is a TEM. And these are the antibacterial zones. The zone diameter increased with increasing metal salt solution concentration here. So this can be used for antibacterial dressing materials as well as the antibacterial packaging films. So to widen the applications of these nanocomposites, so instead of films, we thought the fabrics will be having more applications, antibacterial applications, and then the medical applications and so on. So in the earlier process, while we making these particular films, nanocomposite films, we used the leaf extract as the bio-reducing agent. Then we thought, suppose if the matrix itself is having some chemical groups, can we exploit this without using the external leaf extract? Yes, we tried them in one single step, and that is known as the hydrothermal method for the in situ generation of the metal nanoparticles inside the cloth, inside the fabric itself. Because the cellulose is having hydroxyl groups, many hydroxyl groups, which can also reduce the metal salt solutions into the corresponding metal nanoparticles inside the fabric itself. But at room temperature, it takes a long time because they're not sufficient. They're reducing groups, as in the case of the this particular leaf extract in the films. So alternately, instead of carrying those experiments, earlier experiments were carried out at room temperature only. So that is why it took 24 hours. But here we want to hasten up the process. So by exploiting the reducing groups that are present in the fabric itself or the hydroxyl groups, for that we carried out this experiment at elevated temperature of 80 degrees Celsius. How we did it? So this is a method, one single step method. You don't require any external chemicals. So this is the metal salt solution at 80 degrees. You require a magnetic stirrer with a heater. So thus the heater is maintained at 80 degrees. And then we dip directly the cloth, white cloth or natural fibers or any material. So if you want to convert that into a nano composite, just dip them and then allow it for 24 hours. Slowly the color of this white, generally we have taken the white fabric, color of this white fabrics changes. The change in color actually, as I already stated, will be an indication of the generation of the metal nanoparticles inside the matrix. So this is the white cloth, for example. After this hydrothermal process at 80 degrees Celsius, the color of this nanocomposite film or fabric will be changed. The change in color preliminarily indicates the formation of the nanocomposite. So here initially we generated silver nanoparticles inside the white cloth. This is using 1 mm, 2 mm, 3 mm, 5 mm and 5 mm silver nitrate solution as a source solution. You can see the color change in the fabric. Antibacterial fabrics we made. They showed very good antibacterial activity. We proved the generation by SEM-TEM methods. I'm not presenting all the details here. But the silver is expensive, so then we generated copper nanoparticles inside the cotton fabric. So here we used 1 millimole to 200 millimole copper sulfate solution as a source. So cloth and the solutions, only these two we used. Similar procedure we used instead of the silver nitrate solution earlier. We dipped the cotton fabric in copper sulfate solution of different concentrations at 80 degrees Celsius. The color change, slight color change, because copper sulfate itself will be having pale blue color. So the color change is there, but not so as in the case of the silver nitrate nanocomposite fabric. Showed very good antibacterial activity. So this can be used for practical in hospital uses. This is already available in the literature, this particular paper. So then one of my students wanted to prepare them using the leaf extract also, because she wanted to carry out the entire experiment in at room temperature. Then she tried, and she used Cassia alata, that is the Tangedu leaf extract, and then she succeeded in preparing these composites, matrix, the white fabric, and these are the composites with color change indicating the formation of this nanocomposite with in situ generated copper nanoparticles. So what is responsible here? The OH groups came down here in the case of the composite. So it showed the OH groups of the leaf extract have reduced the metal salts into the polyphenols, and then other OH groups present in the leaf extract have reduced the metal salts to their corresponding metal nanoparticles. They showed very good antibacterial activity even after different washings. She washed these fabrics for different times, 5 washings, 10 washings, 15 washings, like that, but they retained their antibacterial activity even after 15 washings also. That means we can repeatedly use these fabrics either for apparels or hospital bed materials, pillow covers, or even for gloves because they're all antibacterial, or aprons like this. Then we also tested for water purification purposes. So this is a sewage water initially, and she kept this fabric with made same composite fabric with 5 to 250 millimole solution. So where the water became clear here, the color of this water was due to the bacteria that is present, and these bacteria is killed. As a result, the water became almost transparent here. So she just suggested these fabrics for the water treatment also. So you can have an additional filter as a cloth filter. As a result, the bacteria can be killed from the impure. And this is a low cost fabric also because only copper nanoparticles are generated inside the fabric and so on. So this work we already published in Preparative Biochemistry and Biotechnology in 2018. If somebody is interested, they can go for all the full details, or you can click them in the Google. That itself will give you the reference. So recently we prepared, especially for apparel purposes, for dressing materials, we generated this silver nanoparticles in polyester fabrics using tamarind leaf extract. Tamarind leaf extract is having many biochemicals, so which can reduce the metal salt to their corresponding metal nanometal particles. This is a matrix, and these are the composites with color change. The matrix was white polyester fabrics, and then the color changed here. So this is a SEM picture of 1 mm and then 5 mm. Spherical silver nanoparticles were formed, and then the silver metal is there. This is a particle size distribution. And antibacterial activity, they showed very good antibacterial activity against both gram negative and then gram positive bacteria. These two are for gram negative, sorry, and for gram positive bacteria. So we suggested them for surgical aprons for medical purpose, for wound dressing, antibacterial textiles, and then bed furnishings for patients in hospitals. So this is about the preparation of the nanocomposite films and fabrics with excellent antibacterial property. This can be used for both packaging, antibacterial packaging, and then medical applications as wound dressing materials and hospital bed materials, etc. And these fabrics can be repeatedly used. We need not use it once and throw away. You can repeatedly use it as your the normal bed sheets and other things, or normal bed materials. For those who are preparing the the ordinary composite materials, maybe using epoxy or unsaturated polyester or any other matrix, polymer matrix, and then some natural materials, especially some people may be using natural fibers as the reinforcement, or some people may be using some waste fillers, natural fillers. So for them, we extended our work for converting those waste fillers into nanocomposites, so that that particular filler will be having the antibacterial activity. For that, we selected three materials. One, natural fiber, Thespesia lampus natural fiber. This is available in Mehboobabaad district of Mehboobabaad. Now itself it is made as a district, I think, which is nearer to Warangal. So it is known as Adavi Benda. This is a forest ladyfinger plant, and it is having very good fiber, the stem fiber actually. That we converted that into nanofiber, nanocomposite fiber, so that that can be used as a filler, so that the hybrid composite which is made with this epoxy as a matrix will become antibacterial. Then we also selected a waste material, namely tamarind fruit shell powder. That also I will show you how we prepared. Then eggshell powder is also converted into a nanocomposite powder. And some of them we got the patents also, especially for the eggshell powder, we got the patent. And for some fabrics also, we got the patents. One Indian patent and then two Thailand patents. I'm not presenting the entire work here because of the patent rules. So this is the Thespesia lampus fiber. This is original fiber treated with sodium hydroxide. It is having the natural color, brown color. But we dipped these fibers in hot silver nitrate solution at 80 degrees Celsius for 24 hours, as in the we described in the hydrothermal process. After 24 hours, the color changes to almost black. The color change indicates the generation of the nanoparticles inside. So how to prove? These are the nanoparticles, silver nanoparticles, spherical nanoparticles are generated inside the fiber. EDX spectra, it indicated the generation of the silver, presence of the silver metal in nano form. This is a particle size distribution. Showed very good antibacterial activity after 24 hours incubation, after 48 hours incubation. Again, it's different. This is against E. coli, Pseudomonas, B. streptococcus, etc. So against both the gram negative and then gram positive bacteria, they showed excellent antibacterial activity. And after 48 hours, the antibacterial activity increased. Actually, sorry, this is a matrix which is not showing any activity, and these are the nanocomposite fibers. This is unmodified fiber, and this is for the modified fiber with in situ generated nanoparticles. This work we published already. If somebody is interested, in 2018, 3 years back, we published this. Then we modified in similar manner tamarind fruit shell powder. This is the tamarind. The shells we will be throwing away. We want to expand this shell and make it as a powder and use it as a filler. for making the polymer composites, low cost polymer composite material. So this is the original unmodified fruit shell powder, and then we generated the silver nanoparticles by one-step hydrothermal method. That means we have taken the silver nitrate solution at 80 degrees Celsius, and then we added this powder and then kept that for about 24 hours. Then the color changed. Color change indicates the in situ generation of these silver nanoparticles. So this is proved by the same images. This for 1 mm concentration A, and then so this is for 5 mm concentration at 25,000 magnification and 50,000 magnification. So these are the shell powder, and these are the nanoparticles. So the shell powder is decorated by these nanoparticles. They're held permanently on the surface here because of the static forces between the OH groups of this shell powder and then the positive charge of this particular metal nanoparticles by electrostatic attraction. And these silver peaks are there, indicating that silver nanoparticles are generated inside the nano composite and so on. This is this particular distribution curve, particle distribution curve. And then antibacterial activity. It showed very good antibacterial activity here. This is unmodified shell powder, and this is modified shell powder against E. coli, and then other bacteria to gram-negative bacteria and gram-positive bacteria. So the unmodified powder did not show any antibacterial activity. One is designated for unmodified powder, and 2 is designated for the nanocomposite powder or modified powder with in situ generated silver nanoparticles. Here they showed very good antibacterial activity by formation of these clear zones. And that this particular eggshell powder I am not presenting. We followed the same method, and then but there are some additional materials we added for as a catalyst and other things we are not presenting. So the applications of this eggshell powder, modified eggshell powder with both the silver and copper nanoparticles, is they can be used for cleaning the household articles, antibacterial cleaning powder, just like Vim. So we prepared low cost this modified eggshell powder with antibacterial activity and so on. What are the applications for this modified natural fibers and fillers? These can be used in any polymer matrix in making biocomposites with synergetic properties of increased mechanical strength and antibacterial activity. So you can convert your polymer composite into a polymer hybrid nanocomposite with antibacterial property by replacing the usual filler by the modified filler with in situ generated metal nanoparticles, and the resulting composite is known as a hybrid nanocomposite with antibacterial property. So this is how we make these nanocomposites and then biodegradable composite materials in our laboratory. So these are some of our students who are involved in this particular work. They're in abroad now, and these two are from Usmani University. I worked in Usmani University for 2 years as a CSIR emeritus scientist. During that process, we developed some of these nanocomposite materials here. And also, presently, I'm working as a visiting professor in Karlsruhe University. There also, I established one nanocomposite laboratory with very low cost. So the entire cost was around 10,000 rupees only, because mainly we use the available materials only for additional things. We sorry about that glass plates, glass tubes, etc. So we used we purchased them for about 10,000 rupees and established a lab. So our main aim is to use low cost methods with available things in the laboratory itself. So this is thank you very much. Because of my throat problem, so now today only I recovered to some extent. So I'm sorry that I could not present the entire thing. That is why, for additional information, you can go through our publications, which are available in the Google. In Google search, suppose if you put my name, A. Varadarajulu, you can get the entire list of publications. And from that, you can browse and then get additional information. Thank you. If there are any questions, I am very happy to answer them.
Sir is requesting to ask the questions or post the questions through his email so that sir will be answerable.
If there are any questions, they can also post now itself.
నేను పోస్ట్ చేశాను. నేను సమ-
I need to thank Varadarajulu sir for your valuable contribution for giving lecture and a beautiful session to all the faculty that helps them to go from general research work into a biodegradable composite materials that not only useful to the faculty to acquire PhD, but also they can, by this a small amount of contribution can be done to the society when they are going for biodegradable composites. So I request all the participants, if you are having still any more questions, you can post it to SAR email address. So I need to thank you to one and all. By this, I conclude this session. Thank you, one.
Thank you, Dr. Kamala.
Thank you, sir. Thanks a lot, sir. Though you are not feeling well, but you have contributed a lot for us today.
Yes.
Thank you, sir.
Thank you so
Thanks,
much. And if it is useful for the students, I will be very happy. And if
Yes, sir.
somebody wants any suggestions, they are most welcome to contact me by email. I already provided my email ID and the first slide itself, or they can contact you for my email ID and other details. So I will always be available for them over internet or over phone also. They can contact me. So now also it is okay to suppose if somebody wants to ask a question, it seems somebody wants to ask a question now.
Please ask the questions.
Sachava.
Hello.
Christian? Anyone can ask the questions.
Okay, they can send to my email also. If they want any suggestions also, they are most welcome. So I can share my experiences and give some sessions also.
Okay, thank you to one and all. And attendance was posted to your website. And tomorrow's class will be sent at what time? And I think it is around 10 o'clock tomorrow's class. But the Google link will be the same. ఇదే గూగుల్ లింక్ రేపు 10 గంటలకి కూడా ఉపయోగపడుతుంది. అదే సేమ్ ఫర్ కంప్లీట్ 5 days. This link is only we are going to use to for the video classes. Okay. Thank you to one and all.
Thank you. Can I switch off?
Yes, sir. Yes, sir.
Okay then.